last class. If you have any doubts and questions, you can ask. Of course, you are always welcome in my office. So, if you have any questions and doubts later, you can come and ask. Yeah, but are there any questions, doubts for now?
Excuse me, sir.
Yeah, yes, please.
Sir, can you please briefly explain about when you will be conducting the exam, sir?
Exam is, I think, as per the schedule. No? So, it is scheduled on 8th of April, and the timing given is 8:15 to 10:15. And the room is LH 621. So it is going to be offline, in person exam. And timing maybe, let me see. Although it is given 8:15 to 10:15, maybe I might extend by half an hour or so. So instead of 2 hours, it might be for 2.5 hours. So 8th of April, 8:15, starting at 8:15. Room number is LH 621. And the syllabus would be the entire syllabus, although there would be a weightage maybe more for the portion which is covered no after minor. So okay, if there are no other questions, so let me start.
Sir, you will be provided with formula sheets.
Yeah, I will be providing formula sheet.
And the types of question will be similar to minor, all numerical.
Yeah, it would be similar to minor. Yes.
The total marks for major and the pre-major total marks can we get?
I think you have the major marks with you. You have the although the weightage, you have weightage also, so because no assignment 3 is not graded, so I cannot do unless that is graded. So but you have the minor marks, you have the assignment marks, so everything is there with you. Minor assignment
Sir,
marks, you can see.
can you please tell the weightage, sir, once again?
Weightage I had declared no in the first class itself. I think the weightage is so minor weightage is going to be 30%, major weightage would be 50%, and the assignment would be 20%. So 30, 50, and 20. Okay.
Yes, sir.
Okay. So then let me start. If there are no more questions. Yeah. So today the last topic which I am going to cover is actually buckling. Okay. Is my screen visible?
Yes, sir, it is
Hello.
visible.
Okay. So let
Sir,
me start. Yeah. Yes,
few
please.
minutes.
Hmm.
Sir, last 2, 3 lectures we have not solved any examples. So if we can have some example problems, than new topic.
So I think I had clarified on that. No, the example problems on plate bending elements and 3D elements, because they are very the matrix sizes and all is quite big. So manually they cannot be done. So for no, I can ask only what no you what can be done. So the derivation and the smaller parts of it. So whatever we have discussed so far, all the concepts are applicable to these problems also. Only thing is that they are a bit more lengthy.
Yes, sir. So for exam point of view, what should we learn or what should we read about in these topics?
from the example, you have to learn the concepts which are taught, all the concepts which are taught over there. And the smaller things you should be able to do the way we have done the other problems, 1D and some of the simpler 2D problems.
Yes, sir.
Yeah. So now I'm going to the last topic I'm going to cover is buckling, that is stability of a structure. So although I will not discuss, I won't be able to discuss all the cases, but the simple illustration I will do through the column buckling. So suppose you have a this column, and although showing it as a horizontal member, but basically what we are seeing here is a column. So this side is a movable support, and then it is subjected to an axial force P. So because this is movable, so we can apply the axial force P and say this is the x coordinate and this is the y coordinate, and the flexural rigidity of this beam is EI, and of course the total length of the column is say L. And now if this load P, so you would have done of course the very basics of this buckling in strength of materials course or solid mechanics course. So now see what happens is if the beam is slender, so one is that for because the cross section is very small, so the stress is going to be sigma xx is going to be P by A. So if the beam is a slender beam, that is length is much larger than the cross-sectional dimensions, then before this sigma xx, which is P by A exceeding the yield stress, the beam will deviate from its straight configuration, and that we call as a buckled configuration. So this beam might take a shape like this. So finally, the beam would take a shape like this, and of course it would move axially also. So finally, the beam might be taking a some shape like this. It will come over here. So this is what we call as buckled configuration of the beam. And we want to basically find out that at which load beam can take this configuration. So now what we say is on and so the condition is that if P, that is the
Excuse
load
me,
P, of course, yeah, yes,
sir. There was one request,
yeah, yes, please,
not regarding this topic. Sir, in for the weightage which you have told 30, 20, and 50, sir,
yeah.
we have done assignment for about 200 marks. So, is it possible that if we can increase the weightage of assignment,
No, no,
can we?
that weightage will be fixed, what I had declared at the beginning. So, because
Yes,
no, if you do those assignments, you also learn how to solve problems, and that is also helpful in the minor and major. So, in a way, actually, by it accounts for the efforts you are putting in over there. So, the weightage I will keep 20 only for the assignment. So, now if P is less than P critical, no, so this P critical we call it as a buckling load. So if this load is less than P critical, and also yeah, of course this stress, sigma xx should be smaller than the yield stress. So that is also an additional condition. Then the beam remains straight. So the beam remains straight, and we also say that the straight configuration, that is straight configuration of the beam, straight configuration is stable if load is less than that. Stable in the sense that if we apply a small disturbance, transverse load or any kind of a disturbance, the beam will come back to its straight configuration. But if P is greater than or equal to P critical, then the beam will take the bend configuration. Beam takes bend configuration. And we can say in this case, because no, the straight configuration of the beam is actually unstable, so a small disturbance, either a transverse load or some disturbance in the boundary condition, will take the beam from the straight configuration to the bent configuration. So that is straight configuration. Straight configuration is unstable. Given a small disturbance, it will go to the bent configuration. P critical, in the here P critical we call it as actually buckling load. This the P critical at which this stable straight configuration switches from stable to unstable. We call that as the critical load or buckling load, or the load at which it takes the bend configuration. We call it as basically the buckling load of the column. And now for developing the element level governing equation, one thing I need is the axial shortening of the beam, so our column. So I'm using the column and beam interchangeably, but when the axial load is there, we actually call it as column. So the if we look at the buckled configuration, buckled configuration means when it has taken a bent shape. So if you look at the buckled configuration of the beam, so this is the straight configuration of the beam, and of course these are the coordinate axes x and y, and then the beam takes some shape, buckled shape, say like this. Yeah, so the beam takes this shape, and so what we can do is, in the beam, if I take this differential length, this length is, let us say, d of x. And the same thing when I consider this deformed configuration, this one. So if I draw the bigger view, and of course this displacement, so originally this point was here and it has moved to this location, so this displacement we call as axial shortening. Axially, basically the beam has moved, so we call that as axial shortening, and let me denote it by delta, this axial shortening. So now we want to find out the expression for the axial shortening of the beam. So as you see, this is the bent configuration of the beam. So if I draw the exaggerated view of this part, so I will have that part is like this, and the horizontal distance between the left side and the right side is d of x. This is the horizontal distance, and the vertical separation is going to be basically differential change in the vertical displacement v. So this would be dv, and the length along this direction can be taken as ds. So for small lengths, you can say that ds square would be equal to dx square plus dv square. So now if I want ds, that is this length, so then the ds is going to be, now you can write this term square root and then take dx common, so you get 1 plus dv by dx whole square, square root of this dx. So you can write this. Then the differential axial shortening, because this is due to differential length delta x, so the axial shortening is because whatever the length of the beam was there, that has become now this curved portion because of this differential deflection delta v. So essentially that difference is what goes as the axial shortening. So whatever the difference between this distance and this distance is the axial shortening. So the differential axial shortening, so if I write that as d of delta, so that is going to be basically ds minus dx, the difference of these two. So because initially the beam was straight, now it has become curved. So to account for that length, the end has to move, so that displacement or moment is ds minus dx, and ds we have already written as 1 plus dv by dx whole square root dx minus 1. So now this can be written as d of delta. Now we can use the Taylor series approximation for the first term. I know that minus 1 is actually dx. So this is d of x. So delta d, if we use the Taylor series approximation and take the first two terms, so then this can be approximated as d of delta can be approximated as using the first two terms. So we will write no the Taylor series expansion, or you can say binomial theorem. So it will be half 1 plus half dv by dx whole square, and then this minus 1 is there, so let me write minus 1 and then dx. So you can say that ultimately this is half of dv by dx whole square dx. So this is d of delta, and then if we integrate it over the entire length, beam length from 0 to L, so we will get, by integrating this, the total axial shortening delta would be integration 0 to L half dv by dx whole square dx. So this is the axial shortening. We will be using this in the for writing down the total potential. Yeah, yes, please.
So can you please explain the term d delta, the axial shortening? D
So the
delta is
axial,
ds minus
yeah, d delta I have written it as ds minus dx. So as I explained here, that when no this is initially the straight beam, then it buckles and takes this curved shape. So when it takes the curved shape, because the total length is same, so this end has to move. No, this end has to move. So that whatever is the displacement of this point, no, this side, where the load is applied, which is actually in the end which is actually free to move, so that would get displaced by an amount of delta, total displacement. So now what I am saying is essentially the same thing here, that basically that this displacement is the difference of, because initially it was straight length, so it was of higher length, but it has taken a curved shape. So this end has moved by that some distance, and that distance is ds minus dx. So the chord length minus this initial straight length is actually not axial shortening d delta. So that is how I have written this as. So actually, it's more appropriate is to think of this like this, that this is in the curved configuration. Initially, if you look at this was some shape like this. So initially, this end was somewhat higher. So this is dx. Finally, this length is ds, and there is difference between these two distances is basically the axial shortening. Okay,
yes sir,
so
yes
is
sir.
you can visualize more over here. So if you look at no this curved shape, so because we are assuming that length of the beam is nearly remaining the same, so no the curved shape no is accommodating greater length over a smaller projection on x-axis, and that requires no this thing to move in this direction, and then whatever is the movement that we are calling as delta, and then no the differential change in the differential axial shortening is given by ds minus dx, and that is what I have written finally as total delta as half dv by dx whole square dx. And then now let's talk of a beam finite limit. So beam, no, the same beam finite limit which we have discussed. So Euler-Bernoulli, of course, based on the Euler-Bernoulli beam theory. So although the similar formulation we can do based on the Timoshenko beam theory, Euler-Bernoulli beam theory. So this beam we are taking, basically there are actually two things. Initially the axial load is applied, so beam would deform axially, so that is known as the pre-buckling deformation. So we are not doing the finite element formulation for calculating the pre-buckling formulation, although it can be done for that, but we are only doing for the post-buckled configuration, so just after buckling. So let us say this is the element, This is the local coordinate system capital X and Y, and these are the local node numbers 1 and 2. And all the concepts which we were discussing earlier would be applicable here. So now for this beam element, first thing is to write the total potential energy functional. So the total potential energy functional is going to be consisting of strain energy and the potential of externally applied load, that is P. So here for writing this, what we are taking is the datum for the potential energy as the axially deformed configuration. So the axially deformed straight configuration. Axially deformed straight configuration of the beam, that we are taking as a datum, which is also, you can say, basically the pre-buckling shape. So for that, the total potential energy functional I would be strain energy. So for the Euler-Bernoulli beam, we know the total potential energy and is strain energy. So length of the element is L. So we will be integration from 0 to L, and then we have EI, which is flexural rigidity, into d2v by dx square whole square dx. So this we have done actually earlier. Now the additional part is, no, there is going to be work done by this force P. So here if you see, this force P is applied. So you apply this force P, and then in the direction of force P there is displacement by an amount delta. So the work done by P is P delta, which is positive. So the potential would be actually negative. So we will have essentially minus P delta, and then that is minus P, and delta is again integration 0 to L and half dv by dx square dx. So this is basically P delta term. So the work done is delta is given by this expression. Now only thing is the local coordinate x is replaced by local coordinate capital X, and the length is a capital L is replaced by small l, length of the element. So this is the total potential energy functional. In addition to this, of course, you will also have to account for the internal forces acting on the left and the right end. So that will be minus, and then we will have v1e, theta 1e, v2e, and theta 2e transpose into shear force at the left end. So minus s1e for the element, bending moment at the left end, and the shear force at the right end, and the bending moment at the right end. So this is the potential of the essentially the internal forces. So this one you call as nothing but your dE. So this is d transpose, and this we call as f internal for the element. So this is the total potential energy functional. And as you see, again the highest order derivative of V in this is second derivative, and the Euler-Bernoulli beam theory. So the primary variables would be V and dV by dx. So we'll have to have V and dV by dx as degrees of freedom at the end node. So there would be total 4 degrees of freedom, and so the interpolation would be based on the Hermite interpolation functions. So now if you look at the interpolation, so we have discussed this. We are the same Euler-Bernoulli beam finite element. Only thing is, earlier we had a transverse load, now we have this axial load, and then the potential energy of this axial force. So that's the only difference. So we had this H1 B1E, and you keep in mind that here, let me define. So theta 1E is nothing but basically dV by dx at node 1, and theta 2E is nothing but dV by dx at node 2 for the element. So now if you look at V is H1 V1 plus H2 V no sorry H2 theta 1 E, H3 V2 E, and H4 theta 2 E. So this is the same Hermite interpolation function which we have defined earlier. So I'm not writing that. So somewhere in your notes these are already there. So here HI are Hermite interpolation functions. So now, yeah, so you know that no, you can look for the expressions for H1, H2, H3, H4 in your notes on the Euler-Bernoulli beam theory. So only thing is, no, this expression what we have written, we can always say V equal to H into dE, where no H matrix H is nothing but this H1, H2, H3 and H4, and then in the total potential energy functional we also have d2v by dx square, so that can actually be written as b into de, and where b, as you know, will be second derivatives of these shape functions. So d2 h1 by dx square, d2 h2 by dx square, and so on, or d2 h4 by dx square. So this is your b. So now if you substitute this in the integral functional I, so finally we will have now the element level governing equations. The procedure is same. No, so I am not explaining that. So first term you have to write ei d2v by dx square transpose into d2v by dx square, and similarly this term you have to write dv by dx transpose into dv by dx. So you also need one more thing. So let me define before I move write down the element level governing equation. So one more variable you have is dv by dx now. So dv by dx would be first derivatives of the shape function. So let me call simply that as hx into de, and where this hx notation I am using for the first derivatives of the shape function. So dh1 by dx, dh2 by dx, dh3 by dx, and dh4 by dx. So this is hx. So now if you substitute all of this in the I, and then take delta I equal to 0, that gives you the element level governing equation. So if you look at the element level governing equation for this buckling problem, and this comes from basically delta I equal to 0. So the now the form of the element level governing equation is going to be basically first term is same like what we have got earlier, ke into de, that will give you the stiffness matrix. But then the second term, which is p by 2 integral 0 to L dv by dx whole square dx, so that gives another additional matrix, because it will give you matrix. It would be coming from integral 0 to L hx transpose into hx. So that gives an additional matrix. We call it as a geometric stiffness matrix. So we will have P there, and then kge. Kge is for the geometric stiffness matrix into de is equal to F internal. So this will be the element level governing equation, and you already know that here where ke is nothing but integration from 0 to L ei b transpose into b dx, and if ei is constant being in the element, so you also know the stiffness matrix for the Euler-Bernoulli beam finite element. So it is the same thing, ei by L cube, and you have 12 6L minus 12 6L. So these we have discussed earlier. So this is the same stiffness matrix, minus 6L, then 2L square, and it is symmetric. So let me, yeah, so minus 12 minus 6L, then 12 minus 6L, and then you have 6L 2L square minus 6L and 4L square. So this is the same stiffness matrix which we have used for the Euler-Bernoulli beam element. Now the additional thing is no, and we call this stiffness as basically the structural stiffness matrix. Structural, so it's same stiffness matrix which we have discussed for Euler-Bernoulli beam element. We call it as structural stiffness matrix because we have another matrix, so that is why we want to differentiate these two. So the other one is this kge, that is known as geometric stiffness matrix. That would be integral 0 to L, and you will have hx transpose into hx. So yeah, you will have hx transpose into hx dx, and this now if you do the multiply, and so it will be 4 by 4 matrix, and you carry out the integration. So this comes out as 1 upon 30 L, and the elements are the inside minus 36 minus 3L minus 36, 36 minus 3L minus 36 minus 3L, then minus 3L 4L square, 3L minus L square minus 36 3L 36 and 3L. So this comes from the same basically the integration, minus 3L minus L square 3L and 4L square. And this we call as the geometric stiffness matrix. Why geometric stiffness matrix? Because it does not involve material properties. As you see, it's only involves the say functions and their derivatives and integration with respect to length of the element. So it's only the property of geometry. So it is known as the geometric stiffness matrix. And this matrix comes in the buckling problems. And to be more specific is for the eigenvalue buckling problems. So once we have developed the element level governing equations, we can look at the some examples. So so the first example I'm going to take is example 1. So let us say we take the same beam, but we are interested in finding out the critical buckling load now. So this and this you have done in your strength of materials. So now this is the support conditions. This side is movable, and then there is an axial force P, and length of the beam of course is L, and the flexural rigidity is EI. We want to find out the critical buckling load using one element. Although no, from the convergence point of view, you would require more elements. But first to demonstrate, let us model this beam using only one element. So this is element number 1, and this is a local node number 1. This is the local node number 2. So then you would see that the assembled element level governing equation is going to be, because there's only one element, so that is going to be basically this equation as it is. Only thing, the degrees of freedom would be replaced v1 theta 1 and v2 theta 2, where ke is going to be this matrix and kg is going to be this matrix. So now if you look at the boundary conditions for this case, for the single element discretization, so the boundary conditions would be at left node, because the beam is not allowed to move in the transverse direction. So V1 would be equal to 0, but it is allowed to rotate. And similarly at the right end, again it is the end is not allowed to move along the y direction. So V2 will also be actually equal to 0. And then additionally, because the beam is free to rotate at left end about the z axis, and at right end about the z axis, so there is no moment acting at left and the right ends. So we will have m11 will be equal to 0, and also m21 would be equal to 0. So out of these degrees of freedom in the internal force, of course, you as I said over here, you have s1 m1e s2 m2e. So and this v1 is 0, this v2 is 0, so therefore s1 and s2 would be non-zero, but theta 1 and theta 2 are free, so the m1 and m2e are going to be basically 0. So these are the boundary conditions. So now if you look at the total unknowns, so the unknowns are going to be theta 1, theta 2, and of course s11 and s21. So those are the unknowns. But then to solve for the first basically the primary variables, so v1 and v2 they are already 0. The other primary variables are basically theta 1 and theta 2. So what we can do is just take from the assembled system equations, take the second equation is corresponding to theta 1, and the fourth equation is corresponding to theta 2. So take second and fourth equation. So now in that case, what we will get in the left hand side, we have already this EI by L cube, and of course small l is equal to length of the element. So we are taking the second and fourth, no, the second and fourth equations, because v1 and v2 are 0, so when I take the second equation, this will be multiplied with v1, so that is 0. This will be multiplied with theta 1, then this would be multiplied with v2, and v2 is 0, so its contribution will go. So you will get basically 4l square and 2l square, and then you take the fourth equation. So again, this goes with v1, this goes with v2, so they are 0, so therefore the contribution of these terms is going to be 0. So you'll have this 2l square and 4l square. And same thing from the geometric stiffness matrix, we will get this term, this term, this term, and this term. So that means finally you will have this as 4l square, 2l square, 2l square, and 4l square. As I explained, we are only a non-zero degrees of freedom are basically in this case with the single element discretization is theta 1 and theta 2, minus we have p upon 30l. So in the geometric stiffness matrix, this 1 upon 30l is common, and then here you have 4l square minus l square minus l square and 4l square into again theta 1 theta 2. And on the right side in the second and fourth equation we have m11 and m21, and both of them are 0 because at the left and the right in beam is free to rotate, so this is equal to 0 and 0. So what you can do is, no, you can take this term to the right hand side, and let me call this matrix as, no, basically K matrix, and this matrix as Kg matrix. So assembled and after imposition of the boundary condition you have these matrices. So actually, no, this whole thing can be written as K into D, and this vector I am calling as basically D. So Kd, you can write is equal to P into Kg geometric stiffness matrix into D. So ultimately this problem is governed by this equation, and you see this is basically an eigenvalue problem. So what we are discussing is eigenvalue buckling problem. So this is essentially is an eigenvalue problem where D is eigenvector and P is actually eigenvalue in this case. Now as far as the solution is concerned, so what we are interested in, because, no, if you look at in this equation, so essentially, you can combine this and this together, so you have equation in theta 1 and the right hand side is 0, so this is essentially homogeneous equation. So for the non-trivial solution, that is for non-zero solution of D, the determinant of the coefficient matrix must be equal to 0. That is how, you get the eigenvalues. So you need to set up the characteristics equation, and characteristic equation comes from the equating the determinant of the coefficient matrix equal to 0 in a set of homogeneous simultaneous equations. So for non-trivial solution, determinant of the so the whatever you would have learned for solving an eigenvalue problem, same thing is applicable here. So determinant of the coefficient matrix should be 0, and that implies, so if you look at this, so if you look at this, essentially then what it gives you is that k minus 1, we are equating the determinant, we are basically trying to find out the critical value of load. So let me put P critical into Kg. This is the coefficient matrix, its determinant should be actually equal to 0. And now if you look at K and K critical, so this is a basically we are subtracting K minus P critical into Kg. So if you look at the elements of K, we will have essentially determinant of this 4EI. So essentially what you are doing is that you have these equations, you take EI by L cube inside, and then subtract from this matrix, you basically subtract this matrix, and then equate its determinant to 0. So that gives you the eigenvalue. So the first term would be 4ei by L minus 4 P critical into L square upon 30L. So that's the first row and first column of the system equation after assembly and imposition of boundary condition. Then the second column is 2ei by L, and plus we will have P critical into L square upon 30L, and then second would be 2ei by L plus P critical L square upon 30L, and then this is 4ei by L minus 4 P critical L square upon 30L. This determinant must be actually equal to 0. So in this case you find that the form is simpler and the determinant is not this into this minus this into this, and both these terms are identical. No, this term and this term, they are identical. So you can essentially say that 4ei by L minus 4 P critical L upon 30 square minus this 2ei upon L uh, plus this P critical into L upon 30 square, this must be equal to 0. And now see, from this equation we will be able to find out what should be P critical, and that's the condition that no, the P has to equal to P critical, and if it is so, then only theta 1 and theta 2 would be non-zero. That means the beam will take a bent configuration, buckled configuration. So now what you can do is, if you look at you need to solve these equations. So if you see, this is in the form of a square minus b square, so you can factor it out for finding out the value of P critical. So a square minus b square can be written as a minus b into a plus b. So no, that is no, if we do a minus b, that means this term minus this term. So you will get basically 2ei upon L, and this is already minus this term, so it will become minus 5 P critical L upon 30. So this is one term. No, and of course, so that is a square minus b square, we are writing basically as a minus b into a plus b. When you do a plus b, that means this term plus this term, so you'll get 6ei by L, and then this minus and this plus, so we'll get minus 3 P critical L upon 30. This is equal to 0. So this gives you two, this is basically, if you see, this equation is quadratic in P critical. So we will get two roots. So the two solutions are, one is P critical, let us say one root is P critical 1, I am saying, and that would become 12ei by basically L square. And from the second term, equating it to 0, because no, this whole thing is equal to 0. So one possible solution is that this is equal to 0, and this is equal to 0, and that gives you P critical values. So this will come as 60 ei by L square. And as you know, basically this small l is equal to capital L, length of the beam. So a lowest critical load is coming as 12 ei by L square, and that is what we call as a buckling load. So this, using just one element, we are getting the critical value, which is 12 ei by L square. And the actual solution, the exact solution, we know exact solution. So if you recall, the exact solution for this, for P critical, the lowest buckling load, say I'll call it as P critical 1, is pi square ei by L square. And the value, if you look at the value of pi square is 9.8696. I just write the four up to 4 decimal places. This is pi square value. So you can see just one element gives us very the critical load which is close to exact solution, that is pi square ei by L square. But if you take say two elements, you would find that the result is going to be very close to this. So that is the same problem if you discretize using two elements. You will get the very close result. And actually two element means what you can also do is model only half of the beam. And then of course, if you take two elements, so then there would be four non-zero degrees of freedom, theta at the in nodes, and that is say theta 1 and theta 3, and v and theta at the center nodes, say v2 and theta 2. So theta 1, v2, theta 2, and theta 3, there would be four unknowns. So the coefficient matrix would be 4 by 4. So then if you try to solve that, you will get quartic equation in p critical. So that needs to be solved. So that would be more involved. So no, you can do two element simulation actually by doing one element for half of the beam. So this can be simulated no only half of the beam. You model using one element, so node 1 and node 2, and of course the length of the element is small l, which would be equal to capital L by 2. Small l would be equal to capital L by 2. But then the boundary conditions, this is supported in. So if you look at, no, if you're just using one element, I'm saying only r one element in half of the beam. So you are going, I know you are trying to exploit the symmetry. So if you look at the boundary condition in that case, so you will still have v1 equal to 0, and then corresponding m1 would be equal to 0. And because this is the center point v2, so the beam is going to buckle symmetrically. So when the beam buckles, because the supports are identical, so if you look at this center, the slope is going to be 0. So you will have basically theta 2 equal to 0. So in this, the unknowns would be, of course, theta 1 would not be equal to 0, and v2 would not be equal to 0. The additional conditions would be that at the left end moment would be 0, so m1 1 would be equal to 0, and the right end you have again basically shear force is essentially going to be 0 at the center. So you will have S21 will be equal to 0. So then it's a single element, same solution. Small l is of course L by 2, and then you will have finally the equation in terms of unknowns theta 1 and v2, and you will get 2 by 2 equations, and then take the determinant of the coefficient matrix equal to 0. You will get quadratic equation in p critical. Solve for that, you will get the critical buckling load, and you will find that that will come out close to very close to this particular value. So yeah, this is no, this you try to complete. So this is like a homework problem, so you have to do on your own this part. That's a single element solution. I have already given you the boundary condition. So essentially you have to take the second equation and third equation. So earlier we were taking second and four. Now because we are taking modeling only the from left into the center of the beam, so we are taking the non-zero degrees of freedom are theta 1 and v2. So we take the basically second and third equation. So take the second and third equation, take the coefficient matrix, equate its determinant to 0, you will get the critical value, the critical buckling load. The second is, now let's extend the same thing, and if you have any doubts, so you can please ask. So now the second example, what I am doing is, let us say we have a beam which is actually fixed beam, but axially it is allowed to move one side where the load is applied. So this end is fixed, and this end of the beam is on this kind of a support. So it is free to move axially, but it is not allowed to rotate and translate, and there is an axial force P, and we want to find out basically critical load again in this case. So if you, in this case, if you model this using only one element, so because both ends v and theta are 0, so we will not get any basically non-zero equation with non-zero v and theta. So we have to model this using at least two elements. So we'll have to model using two element means, let us say this is the node number 1, this is global node number 2, this is global node number 3, and this is element number 1, this is element number 2. And we are taking of course the length of the each element same, small n and small l, and you would see that small l is of course going to be L by 2, the total length of the beam. So we want to solve this using basically two elements. So now if you look at the assembly, so the assembly is same the way we have been discussing earlier, but let me again revise that. So if you look at the assembly, so there are now three nodes, so there are total 6 degrees of freedom for the discretization as a whole. So I am saying V1 E is nothing but V1, theta 1 1 is nothing but theta 1, and at the center node V2 1 is equal to V1 2, and theta 2 1 is equal to theta 1 2. So and those we are calling as V2 and theta 2, and then the third node is V3 and theta 3. So this is the one matrix you have, and then you have the other matrix which is basically the geometric stiffness matrix. So assembly of that. So this one, you know, this EI by L cube is common, and when you assemble the first element is going between nodes 1 and 2, so it will go into the first 4 rows and columns. So we will have 12 6L minus 12 6L, and then here we will have 0 0, and then 6L 4L square. So I'm just taking the first element contribution to this 2L 0 0, and then we will have minus 12 minus 6L 12 minus 6L, and then we will have here 6L 2L square, then minus 6L 4L square. So that's the contribution of basically the first element. Second element will go into the basically third, fourth, fifth, sixth rows and columns. So its contribution would start from here. So here we will have plus 12, and then we will have plus 6L, and then we will have minus 12 and 6L. Then here we will have again plus 6L plus 4L square, and minus 6L 2L square. And then the third row of course will go here, minus 12 minus 6L 12 and minus 6L, and this will be 6L 2L square minus 6L and 4L square. These terms would be 0 and 0. So this is the assembled stiffness matrix. So I know the same thing we will have minus that geometric stiffness matrix assembly. So we have P upon 30. Let me write in the same color. So we will have P upon so we will have P upon 30 L common from both the elements, and then the inside again geometric stiffness matrix is also going to be of size 6 by 6, and here the same V1 theta 1 V2 theta 2, but now you are dealing with two matrices, so that's the only difference. Otherwise it is same. So the first element P by 30L is common, so inside you get 36 minus 3L minus 36 minus 3L geometric stiffness matrix minus 3L 4L square 3L minus L square minus 36 3L 36 and 3L and minus 3L, and this same what I have written already, the geometric stiffness matrix for one particular element. So this is a contribution first element. The second element contributions will go to third, fourth, fifth and sixth rows and columns. So it will start from here. So here you will have 36 minus 3L, and then you have minus 36 and minus 3L, and here with this you will have again plus 3 no minus 3L, not plus. Second row of the first element, so minus 3L, and here we'll have plus 4L square, and then 3L minus L square, and then we have this minus 36 3L 36 and 3L. The last row is minus 3L minus L square. So you keep in mind that no, these terms are together, these terms are together. Similarly, these terms are together, These terms are together. So minus 3L minus L square, 3L and 4L square, and these would be 0 0, and these will also be 0 0. So this is the assembled. The right hand side what you will have is, so this will be equal to, so the right hand side if you look at this side you will have minus S11 minus M11, then you will have S21 minus S12, you will have M21 minus M12, and then you will have basically S22 and M22. So this is the assembled system equation. And this assembly procedure is same what we have discussed earlier. There is no difference actually. Now if you look at the boundary conditions, so that is what is important. So if you look at the boundary conditions, so beam is fixed at both the ends, so that means v1 would be equal to 0, theta 1 would be equal to 0. At the left end the beam is fixed, so v1 is equal to 0, theta 1 equal to 0. And similarly the right side beam is fixed, so it cannot have any transverse deflection, so v3 would be equal to 0, theta 3 would be equal to 0. And additionally, because there is no concentrated force applied at the center node, so this will be equal to 0, this will be equal to 0, so you will have S21 minus S12 would be equal to 0, and M21 minus M12 would be equal to 0. So these are the boundary conditions. Now we want to set up the equations in terms of unknown. So now if you look at in these equations, so v1 and 0, theta 1 is 0, v3 0, theta 3 0. So in terms of displacement, only unknowns are basically v2 and theta 2. So to set up the equations for v2 and theta 2, we take the third and fourth equation. So now we call this equation as, say, I think I haven't numbered any equation so far, so let me just say equation 1. So now if I take equations 1 of 3 and 1 of 4, so for third and fourth equations. So now if you look at the EI by L cube is common, and in this equation when we take the third equation, so you have this into v1 is 0, this into theta 1 is 0, then this is 24 and 0, and this is 0 and 8L square. So in the matrix form you will get basically 24 0 0 and 8L square into v2 theta 2. The geometric side will get p upon 30L, and inside we will get 72 0 and 0 8L square. This is v2 theta 2, and this whole thing actually is equal to 0. So again, as usual, now we call this as K matrix, this matrix basically as Kg matrix, and the vector as a D matrix. So for the non-trivial solution, so one solution is that v2 and theta 2 equal to 0, and these two equations would be satisfied by that. So but that is a straight configuration of the beam. We want to find out the v2 and theta 2 and also corresponding p, so that v2 and theta 2 are non-zero. That is, beam takes the buckled configuration. So that is what we are trying to find out. So that we call as non-trivial solution. Trivial means 0 and non-trivial means non-zero solution for v2 and theta 2. So for non-trivial solution, what we will have is then k minus p into kg, the determinant of these two matrices, and for the non-trivial solution p has to be p critical, so I'm putting here p critical. This determinant should be equal to 0, and in this case if you see the off diagonal terms are 0, so this is 0, this is 0, this is 0, this is 0, so only diagonal terms would be there. So you can straight away write the coefficient of the determinant matrix equal to 0. So that essentially gives you 24 EI by L cube. From this we get, and from here 72p upon 32L. So minus we will have 72p critical upon 30L. So that is one term into the other term, and the other term is 8ei by L. So you are simply combining these two matrices together and then equating the determinant to 0. So yeah, that's the straightforward thing to do. So that is 8 P critical into L upon 30, and this must be equal to 0. So this is a determinant, and this determinant should be equal to 0. And now if you solve, so we can say that this is separately equal to 0, this is separately equal to 0. So if you solve actually this, so you get two values. One is, let us say, call it as P critical 1. So if you solve from this, the equating this equal to 0, you will get the value of P critical 1. So that comes out as actually 10 EI by L square. And from this equation, another equation, that is this term is equal to 0, gives you say P critical 2, and P critical 2 comes out as you see 30 EI by L square. And now if I substitute this small l is equal to L by 2, I will get P critical 1. Actually no, this will become 40 EI by L square. That's the lowest buckling load, and which is of interest to us. So that's the lowest buckling load which is of interest to us, and that is 40 EI by L square. Now if you look at the, I know you would have done that in your strength of materials course, you know that uh, P critical for the exact solution, the lowest buckling load, it comes out as P critical 1, the lowest buckling load comes out as 4 pi square EI by L square for fixed beam. That is beam which is not allowed to move in the transverse direction and not allowed to rotate, has the buckling load as 4 pi square EI by L square. And if you look at 4 pi square, value is approximately 39.47. So almost 40. So you see, just two element solution where we are just solving two equations in V2 and theta 2, we are getting the critical load almost close to the exact solution. So the advantage of finite element, so of course these are the problems, simple problems through which I can demonstrate the applications. So we'll see for these simple problems we are able to get the very accurate solution. And suppose if you go for 3 or 4 elements, you will exactly get this 39.47 up to 4 decimal places no accurate result you will get. So this is how, and of course you can solve, you can have any boundary condition along the length, the beam kind of have variable cross section. So all that can be easily handled using finite element method, and you can find out the critical load which is of interest in designing. So if the beam is slender, it may not fail by no, the material failure may not take place. That is due to stress exceeding the yield stress of the material and things like that for ductile material, and ultimate strength for the brittle material, but it might fail by buckling. And ultimately, of course, buckling can further be followed by material failure, but initial failure would be buckling failure, which is a geometrical failure, and their interest is to find out the critical load. So then we will have to make sure that the applied axial load, compressive load, is basically less than the critical load, so that beam doesn't buckle, it remains in the straight configuration. So like this, you can also set up the buckling problem for plates, the plate bending element which I have discussed. And because typically, if you look at the submarine, submarine is subjected to external hydrostatic pressure, so that gives rise to basically compressive axial stresses and compressive hoop stresses, and those compressive stresses lead to buckling of panels. No, that is basically panel supported between different stiffeners. So there can be local buckling or global buckling. So there you need to do one simple thing to do is the eigenvalue buckling analysis. So the same concept is applied, although the element type would be different. So the form, shape, and size of the structural stiffness matrix and geometric stiffness matrix would be different, but the solution is going to be basically similar. So I think this is what no I wanted to discuss in this stability, because within the limited time, this is what actually I can do. And next is, I had promised that I will discuss some case studies. So now let me discuss that. So I will. So meantime, if you have any question on whatever I have discussed, so you can ask. So no, you should be able to, for different boundary conditions, different number of elements, you should be able to basically set up the equations, and no, from the equating the determinant of the coefficient matrix, you should be able to get the buckling law. So are there any questions, doubts on this, whatever I have discussed today? Okay, so then yeah, then let me close this and open the PPT file, for I will share a few examples.